All right, so what do we want to say about elimination reactions? Well, first of all, I want to give you three quick mechanisms that you can form an alkene. If you don't remember, in elimination reaction, you eliminate a small molecule. You get rid of a small molecule in order to make a double bond between two carbons. So in order to make an alkene. And so there's three mechanisms that we're going to go over. We're going to focus on one of them today, but I'm just going to introduce the other two as well. And that one of those is the E1 reaction. Of course, E stands for elimination and the 1 stands for first order. And the reason why it's first order is because you form an intermediate. So the first thing that happens is you break that carbon halogen bond, that CX bond. Remember, X is just the generic symbol we use for elements in the, the halogens column of the periodic table. So chlorine, bromine, iodine, whatever. And so that bond breaks and you create a carbocation. That's the intermediate. So that's the first step. All right. So again, this would happen in 2 steps. If you want to add that to your, to your notes there, this would be like step 1. And then after you have the carbocation, okay, you got this carbocation, so it's looking for some electrons. Well, this bond here between the carbon and the hydrogen says, oh, well, I'm happy to provide those electrons for you. You want some electrons? Here you go. So it dumps the electrons into that and makes a double bond, and then that pops off as H plus and combines with a base that also happens to be in the area to give you that compound right there. Okay, so this would be step 2. It's a second step. And just like the SN1, the first step is the slowest step. Formation of that carbocation is the slow part. The fast part is that second step. But we'll get into that next week. Okay. All right. So kind of similar to the E1 mechanism is what we call the E1CB reaction. It's similar in that it happens in 2 steps. And it's similar in that you produce an intermediate that's an ion, but this time it's a negative ion. It's a carbanion, okay? Because the first thing that happens is a base that's in the neighborhood, this B with the 2 dots there representing a lone pair of electrons, it's looking for a hydrogen. It's looking for H+. So the alkyl halide, whatever it might be, is just willing to give up one of those hydrogens on a carbon that's adjacent to a carbon connected to a halogen. Okay, so the base takes that hydrogen. The hydrogen dumps its electrons on the carbon, so it creates that carbanion. It's a negative ion. Okay. And so then a concerted thing kind of happens. So that pair of electrons moves over into between the 2 carbons to form a double bond. And the connection that the other carbon has with the halogen, that pair of electron moves on to the halogen to make it a free halide, like chloride, bromide, iodide. Okay. Because as we know, it's more electronegative, so it's happier to house that negative charge than a carbon is. So that's why it's a favorable, sort of follow-on reaction. Okay, but again, I don't want to talk about this too much. We'll save that for next week, but just wanted to introduce you to this mechanism because the one we're going to focus on today is the E2 reaction. So this is a 1-step process. It does not have an intermediate. And so what happens is you have the simultaneous cleavage of a carbon-hydrogen bond and the carbon-halogen bond, the CX bond, to produce the alkene without intermediates. So all these curved arrows you see happen kind of at the same time. The base interacts with the hydrogen and pulls it in. The electrons between the hydrogen and the carbon move down to between the 2 carbons, forming a double bond. And at the same time, the electrons in the carbon-halogen bond move on to the halogen. And so you get the alkene produced, and you also produce this, the protonated base, whatever it might be. You'll see in just a minute, it's a strong base. And then the halide as well. Okay. All right. So that's what we're going to focus on today is more details about this E2 reaction. Okay. But before we do that, let me just do another example problem that has to do with what we left off with yesterday in our discussion about formation of alkenes through elimination and Zeitz's rules, because that comes into play with this example that I'm going to do here. Okay. It just doesn't really matter what the mechanism is. So regardless of the reaction type, whether it's E1 or E2 or E1CB, let's propose an alkyl halide that could serve as the starting material for this alkene. Okay, that is the only product. So this is our only product. We don't get a mixture of products. Okay, so if you think about it, we showed you in all 3 of those mechanisms that the halogen, and I'm just going to use bromide as it could be a chloride, it could be an iodide, but let's just say it's bromide. That's the usual one. So it has to be on a carbon that's involved in this formed double bond. The double bond that's formed, that halogen was on one of those 2 carbons. So let me just, again, with my poor penmanship, try and draw a couple pentagons here to replicate the original alkene, sorry. Okay. All right, so there's one. I'm gonna draw another one. Okay, so like I said, that halogen had to be on one of those two carbons right there. So it could be the carbon there, that could be where the bromine was before the elimination, or the bromine could be here off this carbon right here, okay, because it has to be one of those two carbons. So let's just think about what the products would be if the bromine is in either of these two positions, and maybe that'll help us decide, which alkyl halide did serve as the precursor, as the starting material to produce this alkene that's shown on the right. Okay, let's do this one down below first of all. So remember what happens is that, essentially you're going to eliminate HBr. So we've got some hydrogens here. We've got two hydrogens here implied. And then right here, we also have another hydrogen that's implied. Okay. Let me change colors real quick to kind of keep things a little bit organized. So if I remove these two atoms right there, right, that would cause the double bond to be right there, which is that's what I want. Okay, that's the actual product that's formed. Okay, so this might be our answer. But the other thing to keep in mind, though, is that I could also eliminate, and let me change colors again, just to, again, kind of try to keep things organized. Let's say that the bromine was eliminated with that hydrogen, because, that's all it takes is just a hydrogen and a bromine adjacent to each other. So that would cause the double bond to be between these two carbons. Okay. Now, that one would actually be favored according to Zaitsev's, oops, let me start it over again with that word, favored, because of Zaitsev's rule says that the more stable alkene will be produced as the major product. And this one would have more substitution. Okay, if it formed this one right here, it's only substituted twice. You got that, it's a di substituted thing. But if I formed the one with the green double bond, so if the double bond were here, so imagine for a second that the double bond's not there, imagine that the double bond is there, that's got a tri-substituted situation, okay, which is more stable. So that's how I know that that's not the right starting material. The bromine here is not the right starting material, because the major product would not be this product that is shown. Okay, so let me kind of erase that. So now, just to prove it to ourselves, let's analyze this one up here. So again, if this is the right position, then there are hydrogens here, hydrogen and a hydrogen, and there are hydrogens here too. I'll talk about those in just a second. But let's say that this bromine and this hydrogen are eliminated and it produces that double bond. Well, that's good, because that's what I'm looking for. I'm looking for that double bond in that position. Okay. Well, what if, and by the way, so what if it went the other way? What if it went bromine and that hydrogen? Okay. Well, that would produce a double bond right there. But flip that like a pancake. So instead of okay, so instead of there, it would be there between the kind of the two upper carbons on that side. But you just flip that like a pancake, and it's the same thing as what is shown. So they are equivalent. There's no difference between those two products. Okay. So the only product, that's why it's, it says in the question, the only product. So the only product possible when the bromine is in that position is correct. All right. So yeah, so the correct answer would be if the bromine is coming off that middle carbon. All right. So the point being is I wanted you to recall a little bit about the Zaitsev's rules that we left off with yesterday. And I've got a small group activity for you guys to try similar to that problem. So talk with your neighbor about this one. So same wording of the question, regardless of the reaction type, propose an alkyl halide that could serve as the starting material if this alkene is the only product. So I'll let you think about that and talk about that. And I'll show you the answer in just a minute. Okay, so here's just some notes. I'll show you a prettier version of the correct answer in just a second. But so the alkyl halide that you should start with has the bromine on that last carbon, on this end carbon, and the reason why is because that's the position you need to put it in order to only produce this product. So if you look down here, if the bromine is in this sort of this interior carbon, right, like right there, then it can form a double bond on either direction. But the major product would be if it forms a double bond between it and the carbon on the left, because that would lead to a more substituted alkene. That would lead to a tri-substituted alkene. And according to Zaitsev's rules, that's more stable. So that's going to be your major product. Okay. Because it would split off with a hydrogen from that interior carbon that would lead to a tri-substituted alkene. Okay, so we're going to talk a little bit more about this mechanism, the E2 reaction. So what brings it on, what causes this type of reaction is the reaction of an alkyl halide with a strong base. Okay, so that's when you look for it. Whenever you have an alkyl halide and in the mix, you also have a strong base, something like, the sodium hydroxide or even something stronger than that. Okay, it is the most common elimination pathway. Okay, and as the abbreviated, name of it gives away, it's a second order reaction. And if you think about the mechanism, it requires multiple molecules sort of working in concert, right? So it's going to depend on the concentration of both of those that are involved, the alkyl halide Rx, as well as the base that you're using, whatever strong base that happens to be. It's a second order reaction overall. So the rate law is that the rate is equal to the rate constant times the concentration of Rx, the alkyl halide, times the concentration of the strong base. Okay, now the other unique thing about the E2 mechanism is that the conformation of the alkyl halide is important. So you got to remember what we mean by conformation. That is the different arrangements of the atoms based on rotations. Okay, so remember that's what we mean by conformation. We're talking about the way the atoms are arranged based on rotations. Okay, so for example, what we're going to look at particularly today are the syn periplanar arrangement and the anti-periplanar arrangement. We'll explain what that is in just a second. But what we have already talked about in previous weeks is, all these alkanes, there's free rotation around these single bonds, right? They can rotate freely around that single bond. And so the different ways that they arrange themselves based on that free rotation is what we mean by conformation. So like this, remember, is called eclipsed because the atoms are just kind of right in each other's way. These two are just right in each other's way. And then the more energetically favorable, the lower energy version, is what we call staggered. Okay, so we got quite a bit of review built into this lesson actually, but this is one of those little review topics, the eclipsed versus the staggered, because that definitely is important with an E2 reaction. Okay, and I got this little diagram is not in your handout, but you'll get similar things are printed in there. So first of all, a definition, because this is the arrangement that we want. It's called periplanar. And it's when the hydrogen atom that's going to leave, that's going to be eliminated, the two carbon atoms that will engage in the double bond, and the leaving group that also leaves, obviously, they lie in the same plane. That's what we mean by periplanar. Okay. And there's two types of periplanar you can have. You can have the syn periplanar, where both of those atoms that leave are on the same side. So H and X are on the same side of the molecule. And we've seen that word used before, SYN, syn, when we talked about the addition reactions. They were like either syn addition or anti-addition. So we've seen that before. Okay, so let me point out, if it's not clear, what I mean by periplanar with this diagram. So you can see from these pictures that these are all kind of in the same plane. So if this, if I were to put all these atoms in the same plane, like the same sheet of paper, that's what we mean by periplanar. Okay. And in this case, they're syn periplanar because they're both, the atoms that are leaving happen to be on the same side. So actually it doesn't happen this way, that you will not get the elimination reaction when you have the syn periplanar arrangement. You only practically speaking, you only get it when you have the next arrangement, which is called anti-periplanar. And so that's when they are opposite each other. So they're all still in the same plane. You could, fit them all on the same sheet of paper, but they're on opposite sides. And it's a staggered geometry. It's not an eclipse geometry. All right, and that's why we say that it happens this way, because we know that the staggered conformation is energetically favorable. It's lower energy. It's more stable. So this is the conformation that will actually facilitate the elimination reaction. Okay, so what goes on is you're going to, according to the E2 mechanism, the base comes along and takes on that hydrogen. The hydrogen gives up its electron pair to form that double bond, and then the halogen pops off as a halide, like bromide or chloride or whatever. Okay. So what's so important about this arrangement is, I don't remember if it's on the next slide. Let me show you. Hold on just a second. Okay, yeah. So this is the required conformation for the E2 mechanism. It will not happen unless you have this arrangement, the staggered anti-periplanar of the hydrogen and the leaving group. Okay, yeah. So this explains why it happens. Because when you've got that anti-periplanar arrangement of the atoms involved, that side-by-side overlap between the orbitals that become available, the carbon p orbitals, that side-by-side overlap is easily to facilitate. It's right there, so it occurs easily. So when the atoms involved in E2 are anti-periplanar, side-by-side overlap of carbon p orbitals in the transition state can easily occur. And remember, that's what a pi bond is. A pi bond is not that head-to-head sigma overlap, right? It's that pi bond is that side-to-side overlap that acts more like a rubber band or a belt holding the two atoms together, above and below the bond axis. Okay. So that's why this is so important, and it's why that particular conformation facilitates the E2 mechanism, because when the hydrogen leaves and the leaving group, the halogen leaves, then those orbitals are right there, side by side, to overlap and to form that pi bond. Okay, so remember that this second bond here is your pi bond. So that's a pi bond, and then this course right here, that's your sigma bond. You got to keep that original connection. You'll never get a pi bond unless you first establish the sigma bond. Okay, so something else about the E2 mechanism that's unique and important is that it is a stereospecific reaction type. Now, what we mean by that is, as you can see in the description there, is that if a given stereoisomer always produces a specific stereoisomer. So you start with something specific and you end up with something specific. It's reliable every time. You're gonna get that. Okay, so let me go through an example to talk about this, to show you what I mean by this. So let's say that we have the meso form, and remember what we mean by meso. Let me actually draw the Fisher diagram to remind you what we mean by meso. Okay, you remember that. So if I were to draw the Fisher projection of this, okay, you gotta rotate. Let's rotate that way so that we can put the two hydrogens right here, okay. So then the two phenyl groups would be on the same side. And remember that the pH here, that's important. When you see that abbreviation pH, it stands for phenyl, which is the word that we use for a substituent that is a benzene ring. And so if you rotate that, then the two phenyl groups would also be right on top of each other, and the two bromine groups would be right on top of each other or right next to each other. Okay, so that's a phenyl. And then the two bromines would be on the same side. So remember that meso means that there's that mirror plane within the molecule. So if I cut this molecule in half, it looks the same up top as it does down below. That's what we mean by meso. It's got that mirror plane. So it turns out when you have a meso compound like this, it always produces the alkene that's got the E stereochemistry. And remember the difference that you got Z and you've got E, okay? And the way, and I don't want to get ahead of myself, but the way in which you designate whether the alkene is Z or E is, first of all, it has to have 3 or 4 substituents. Okay, but then if the higher priority are on the same side, it's Z. If they're on opposite sides, it's E. Okay, so let's think about that. So in this case, let me kind of erase everything I've got up there so far. So as you can see, what I'm getting rid of here is I'm getting rid of this hydrogen. Okay, and this bromine, they're leaving. And so when what's left, you're going to put the hydrogen and the bromine on one side, and you can put the two phenyl groups on the same side, and that's reflected here. You got the two phenyl groups on that side, and you got the bromine and the hydrogen on that side. Okay, so then remember, we use the Kahn-Ingold pre-log rules to decide on this carbon which one is higher priority, which one's lower priority, and we do it by atomic number. So bromine has a higher atomic number than the carbon in this phenyl group, that carbon right there. So this one is the higher priority, this one is the lower priority. And so then I do the same thing on the other side with this carbon. Okay, in this case, it's a carbon on the phenyl versus a hydrogen on the other side. So this is a higher priority. Okay, so since the higher priorities are on opposite sides of this double bond, okay, that's why it's E. Okay, if they were on the same side, it would be Z, but since they're on the same side, since the higher priorities are on opposite sides, that's why it's E. So that's what we mean by this elimination reaction is stereospecific. I started with the specific stereochemistry, it's meso, and I ended up with a specific stereochemistry, E, and that will happen every time. So let me do another example for you. And I've got some skeletal, diagrams here for us to work with on this one. But what we want to do now is we want to consider the product of E2 elimination of 1R, 2R, 1,2-dibromo, 1,2-diphenyl-ethane. So this is similar to the compound that we just looked at, but let me just show you what I'm talking about here. Or I'm not sure if I wanted phenyl or methyl. Hold on just a second. It might be methyl. I may have put the wrong word in there on accident. It doesn't really matter. Okay, so R and R. So I know that I want that stereocenter to be R, and I want this one to be R. So remember what that means. I want the rotation to be clockwise, and an easy way, it's clockwise if the hydrogen is pointing away from us, if the lowest priority group is pointing away from us. So let's go ahead and put the hydrogens, because again, we know that those vertical lines in a Fisher projection point away from us. Remember, I said that this lesson is going to have a lot of review in it. This is another part of that review. When you're looking at a Fisher projection, the vertical lines pointing away and the horizontal lines are pointing toward you. Okay. So if I want it to be R, then I want the bromo to be on this. Okay. And then I want the bromo to, the rest of this is going to be priority 2. And then I'll put I'm going to go ahead and put phenyl, but like I said, it may be methyl. Put pH for phenyl, because this is change colors here, because this is going to be priority 1 because of atomic number, and then this down here is going to be priority 2, and then the phenyl is going to be priority 3, and so that's clockwise rotation. That's like turning the steering wheel to the right. So that's why I can call that R. Okay. So now what do I want to do on this bottom carbon? Well, I want it to be R, right? This is 1R and 2R, so I want both of these to have R configuration. Okay. So what you'll see is if I put the bromine here and I put the phenyl here, then that leads to R configuration on that chiral center, because this would be priority, change colors again. The bromine would be priority 1 because it's got the highest atomic number. Then this group here, that group would be priority 2 because it's got more carbons in it, it's got a bromine in it. And then this phenyl group would be priority 3. And again, if we go from 1 to 2, 2 to 3, and 3 back to 1, then that's a right turn with the steering wheel. That's clockwise rotation. So that's also R. And again, I don't have to flip that because my hydrogen, the lowest priority group, is pointing away from me. A lot of times when we did discuss Fisher projections, we changed it. We did the opposite. We actually selected the opposite because the hydrogen, the lowest priority thing, was not pointing away from you. But in this case, just the way that I've drawn it, it is. Okay. All right. So now I'm just going to kind of translate this over to this dash wedge drawing, because that helps us with the Newman projections, which will help us with the final answer that we're on our way towards. Okay, so these are hydrogen, and then I've got a bromine, I got a phenyl, and then I've got the bromine right there, and I've got the phenyl right there. Okay, so now what I'm going to do is I'm going to, remember how we convert these into Newman projections. It's like if you look at it. So let's say that this is my eyeball. I'm looking at it sort of head on this way. Okay. So that means that the hydrogen is down here and the hydrogen in the back is right there. And then in front, I've got the phenyl and I've got the bromine. And then on the back, I've got the phenyl and I've got the bromine. Okay. But I know that the elimination reaction is not going to occur when it's eclipsed like this. It's going to be staggered and it's going to be anti-periplanar. And so what I want to do is well, first of all, let's draw the rear group the same. Okay, so I'm going to put the H and the phenyl and the Br right there. Okay, but now I'm going to rotate this 60 degrees. So all these are going to rotate 60 degrees. Okay, so that puts the Br up here, and that's important because again, I want them periplanar and a hydrogen there because that hydrogen rotated over there. So, these are equivalent. I'm just doing a rotation here. And then this, that phenyl moves down here. Let me remind you that the reason why I have gotten to this point is because this gives us that anti-periplanar conformation that I'm looking for, the anti-periplanar. Okay, because now, the hydrogen can leave, a base can come along and grab that hydrogen. A strong base can come along, grab that hydrogen. It gives its electrons to form that double bond between the two carbons, and then the bond between the carbon and the bromine, those electrons move on to the bromine to make the bromide. Okay. All right. So then, essentially, what that translates into then is you get, your carbon-carbon double bond, and you've got now it's got the 4 groups coming off of it. All right, and on that back carbon, we'll say that this carbon right here is going to be the back carbon. So I've got bromine on one side and I've got phenyl on the other. Okay. And in the front, I've got the hydrogen on this side and I've got the phenyl on the other. And so the question is, all right, so is this E or is this Z? Okay, so that means I got to go think about the Cahn-Ingold-Prelog rule. So let's compare this carbon right here. So this phenyl is going to be the higher priority, and the hydrogen is the lower priority. Okay, on this side, if I do this carbon, well, the bromine, it's got a higher atomic number, so that's got the higher priority, and the phenyl group would have the lower priority. And so since these are on the same side as, the two highest priority groups are on the same side, then that means I would call that a Z. Okay, so the alkene formed is a Z. So again, this is just an example of the being a stereospecific reaction. Okay, yeah, so we got the dash wedge drawing right there. Okay, and the two Newman projections. Okay, and that leads to the Z. Like I said, that was really just a precursor for this next little topic we got to go over, and that is that, cyclohexane rings, when they undergo these E2 reaction, we have to have the hydrogen and the leaving group in the right arrangement, in that anti-periplanar arrangement. So cyclohexane rings need the extracted hydrogen atom and the leaving group, which is the halogen, to be transdiaxial. Okay. So this is the picture that's already printed there in your handout. So what we mean by transdiaxial, you can see it from the Newman projection nicely. It's just right there. It's periplanar. They're opposite, so anti-periplanar. Okay, and that's what we mean in transdiaxial, because these would both be axial positions. There's the equatorial position. There's the equatorial position. They're both axial. Okay, so we have to have that arrangement in order to get one to leave. Okay, so that forms a double bond as it gets taken off by a base, and then the electrons move on to the chlorine to give us the chloride or the HCl. Okay, but they form that double bond with that mechanism, but it has to be that anti-periplanar. Okay, so let me see here. So if you can't tell, this Newman projection, you're looking down these two carbons. You're looking down that carbon right there. Okay, that's that one, and then this other carbon it's like you're looking down that carbon right there. So this part is this over here. Okay, so if they are not anti-periplanar like this, see this chlorine is not anti to any other hydrogen. There's no hydrogen on the other side. It's a carbon, it's a CH2 group that's on the other side. Okay, so it cannot undergo an E2 reaction. Right, that's the importance of it. Okay, yeah, so as I showed you, this is the periplanar arrangement that must be there in order to get the alkene to be formed by the E2 reaction mechanism. There may be other ways to form an alkene, but in order for the E2 mechanism to take place, it's got to be this way. Okay. All right, and so this one's not periplanar, so it's just not gonna react. All right, I think I've got one more example. Yeah, here we go. So let's say that we've got these two molecules. Now, one of them we've already looked at because we did the clicker question just a minute ago. Okay, so so remember that this one, if this was carbon 1, 2, 3, 4. Okay, when it was trans, when you had the trans, so this is the trans version of this di-substituted cyclohexane, and this is the cis version because they're both on the same face of the cyclohexane, right? These are on opposite faces, pointing down, pointing up. These are both pointing up. Okay, so this is the trans and this is the cis. But remember that this one has got, 2 equatorial. It had 0 axial and had 2 equatorial. Okay, and so this one, it's not going to have the setup that we need to have that anti-periplanar. But this one might. Let's see if this one does. Okay, so again, let me draw a cyclohexane. I gotta refresh my cyclohexane drawing skills here. Okay, and so we think about this. Let's call this carbon 1, 2, 3, 4, and say this is carbon 1, 2, 3, 3, and 4. Okay, so on carbon 1, the bromine is coming up out of the page, right? So that's axial up. So my bromine is actually in the axial position there. And the equatorial down is a hydrogen. All right. And so in this case, on this carbon number 2 here, I've got, you know, an axial hydrogen pointing down, and I've also got an equatorial hydrogen pointing down. So that gives me the setup that I need, okay, to get the anti-periplanar, right? They're both axial. That's what we mean by transaxial or transdiaxial. So this is transdiaxial. Okay. Now let's go ahead and do it. What it looks like on carbon 4, just to show you that this is the more stable conformation. This is the conformation that this compound likes to be in because it's more energetically favorable. So at carbon 4, the axial is down, but the T-butyl is up, and so remember that it's equatorial up. So there's a hydrogen axial down, and then the T-butyl is equatorial, right? And since that's such a large substituent, it wants to be in the equatorial. So if it has to choose which one's going to be in the axial position, it's going to choose the one where the bromine is in the axial position because bromine is actually smaller than T-butyl. Okay, T-butyl is bigger than bromide or bromine. That's what I'm saying. Yeah, is that if there is a chair flip, then this T-butyl would be in the axial position and the bromine would be in the equatorial position. And you can't get the E2 mechanism in that situation anyway, but it's not going to be stable because that T-butyl does not want to be in the axial position. It's less stable because it's such a big substituent because you got to have that anti-periplanar arrangement. So yeah, well, of course I had them already drawn. There you go.